Since we have this parameter, something we call it as a phase ratio, which is nothing but volume of your mobile phase to stationary phase, we will just try to get some physical meaning, or we can try to imagine what will happen if you change the ratio. Say beta is equal to volume of your mobile phase to volume of your stationary phase. So what it says is like, you just imagine, so if we increase the volume of our stationary phase, then if we increase the volume of stationary phase, which means naturally the the analyte molecules will like to stay more and more time, will spend more time in the stationary phase, so naturally your retention time will go up. So if volume of your stationary phase is proportional to your retention time, and you think the other way around, if we increase the volume of the mobile phase, what will happen? So what will happen? Like your solute molecules or your analyte molecules will stay more time in the mobile phase, or the other way around, it will spend less time in the stationary phase. So if we increase the mobile phase, the TR will decrease. So this will give you some general idea, volume of the mobile phase, inversely proportional to your retention time. So these are something that you should understand. So this is not a very tough concept, yeah. Like obviously if the volume of your stationary phase is really high, then obviously your molecules or your analytes are going to spend more time in that column, so which naturally it's going to increase the retention time. So we all know density is equal to mass by volume. So volume will be is equal to mass by density. So let's put it that way. So what we are doing is, like, if we have a big column and if we naturally increase the volume of the stationary phase, or in the other words, if you increase the mass of the stationary phase inside the column, your retention time is going to be higher. And if we do the other way around, if we increase the volume of the mobile phase, your retention time is going to be less. How to draw that? So let's assume we filled the column, half of the column, and let's assume we have a big space where our volume of something, your mobile phase, is flowing on the top. Obviously this is just imagination. Mobile phase will flow throughout the column, so which means your solute molecules will be easily knocked out, and then it will come out very fast. It will elute much faster, so your retention time will decrease. So if you increase the volume of mobile phase, your retention time is going to decrease. So that's the key message that you have to remember in your mind. If I ask some tricky questions in the exam, you have to remember this this basics. This is not even a chemistry. This is like the physics. What's diffusion? What's a concentration gradient? So if you have a large volume of your mobile phase, due to concentration gradient, your solute will naturally move from your stationary phase to solute side. And if you have more and more volume of mobile phase, so you are pushing away very easily your solute analyte molecules from the stationary phase to the mobile phase, due to that concentration gradient that exists. So that's why your retention time is going to decrease. I hope you all get this point. Mhm. If you look at the equation, where is that? Okay. Retention factor, capital K divided by beta. No, I think this is fine. I hope you all understand up to this point, and then I will try to solve a few problems, maybe like a tutorial video, not now. And then now I will go to something we call it as a degree of separation. Whenever we are talking about column chromatography, retention time is obviously important. It allows you to calculate a retention factor and so on. But the purpose of doing column chromatography is not to push your molecules in the stationary phase and observe the retention time. The purpose of pushing that molecule through the stationary phase is to find the conditions at which you can push those molecules at a different time. Say like you push the, if you have a mixture, sample mixture that contains A and B, if you manage to push A bit faster, and if you manage to push the your analyte B bit slower when you compare to A, then obviously they travel at a different pace within that stationary phase. That allows you to separate these two mixtures at the end of your column or at the column exit. So the main purpose of doing column chromatography is to separate this molecule. That's why we are going for this technique, and if possible we have to separate them, like we have to try to find the conditions where we can get the pure product of individual components that makes the mixture that you place at the column inlet when you begin your experiment. I hope you all get up to this point. So what matters is the degree of separation, not the retention time. So the retention time, obviously this is important factor, but this is not the prime factor. This is not the prime factor. Why it is not a prime factor? That's very easy to explain. Yeah? You take a column, you take a chromatographic column. So let's say we have compound A, we have compound B, and we put a mobile phase. Let's say they both of them they absorb, dissolve, absorb, dissolve, and at the time when you observe at the column exit, say t is equal to 10 minutes. Let's assume both A and B exit at the same time. So now we know the TR of A and TR of B. That's both is equal to 10 minutes. And then so what? So we calculated the retention time. And let's say we also injected some tracer compound, tracer molecule. Let's say that elute the column at 1 minute. So we know what's the Tm value, that's 1 minute. We can even calculate the retention factor. So that will be equal to 10 minus 1 by 1. That should be equal to 9. K for A is 9, K for B is 9. So what? So at the end of the day, we get some nice parameters based on the theoretical knowledge that we gain. But did we manage to separate these two compounds? Obviously no, that's the answer. So for whenever we think about column chromatography, the key, the prime factor that we should think is how well we separate these two compounds. If we do the same experiment and if we manage to separate, say at a time 5, when t is equal to 5, we get compound A, and when t is equal to 10, if we get compound B, then this is a perfect and clear separation. So this is what we care about when we think about column chromatography. Yeah? So that's what we are going to study at the moment, something about separation. So the idea of separation is the key factor when it comes to column chromatography. So what we worry about at the end of the day is like if we start an experiment with say A plus B, so what we have to answer is like these two different molecules A and B, do they elute at sufficiently different times so that they can be individually quantified, or it can be identified, or can be collected at the column exit. So A should travel individually and then B should travel individually. So you collect, so this is B and this is A. So at the end of the day you collect B and then you collect A. So there should be a clear separation between compound B and compound A. So this is something which is really important. Yeah? So we know what is a retention factor is. So now we have to know what is a separation factor is all about. So we already know that your retention factor so if we have a, and we know what is a distribution constant or equilibrium constant. If we have this equilibrium constant, if this k value is higher, your retention value, your retention time will be high, and then your retention factor will be high, small k, retention factor will be high. So and we know how to define k value, small k, and we know what is capital K, which is a concentration of solute in the mobile phase to the stationary, concentration of analyte in the stationary phase to the concentration of analyte in the mobile phase. So I hope you all know up to this point. So how to quantify the degree of separation? So the degree of separation, we all know if you get some chromatogram, something like that, say this is for compound B, this is for compound A, we know TR of B, TR of A, just to follow wherever I am writing now. So how to quantify the degree of separation? That's defined as degree of separation. We use the notation alpha, which is equal to K suffix B, K suffix A. So this is nothing but your retention factor of B divided by retention factor of A. So this is how we define a separation factor. And normally if we use some expression like this, alpha is equal to K suffix B, normally the compound which is on the numerator side, that should have that's the analyte which will spend more time in the column. So something like in this case B should have a higher retention time in the column, or the K value distribution constant for B will be higher than for A. So which means A will elute later and B will elute later and A will elute first and B will elute second. So that's how we define a separation factor. Some people they call it this alpha also as a selectivity, but I think according to IUPAC, they prefer to use the terminology alpha is equal to separation factor. So throughout the world this is a common terminology. If I ask you to calculate separation factor, it should always refers to this value. You should calculate your retention factor of B, retention factor of A. From there you have to calculate the separation factor. So I hope you all understand up to this point. And the general rule is something like, if you take a chromatogram, something like that. Say this is your tracer molecule, and this is for compound A, and this is for compound B. So this is A, this is compound B. So if there is a clear separation, normally your alpha value will be high. So we will come back to the number, what number we should target at. But for the moment, you should think, if alpha, higher the alpha value, so better will be the separation between the two molecules. Better will be the separation of the molecules, or better will be the molecular separation. Yeah? I need to go to some English class. Okay, anyway, this is not a language class, yeah. So what we are learning is batch process engineering. The more important thing that we should learn is the topic, the subject, which is shown in the book of modules. And apart from that, chromatography is one technique that you are going to use again and again in no matter whatever the industry that you are going to get the job. If there is no industry in this world, there is no research lab in this world, there is no university in this world without a chromatographic setup. Yeah, at least they will do a simple thin layer chromatography experiment in their lab before they leave any chemistry course, or even or any analytical chemistry course, or any chemical engineer, whatever the degree that if they're going to learn, or even pharmaceutical engineers, for example, they must know what chromatography is all about. And since you are learning an engineering subject, we are touching the engineering part of this particular unit operation. Yeah, so I hope we are going well so far, and we are learning this technique because this is really an important technique, and this technique is widely used for like so many purposes, for purification of small molecules, large molecules like proteins, and also it's used in almost every industry, yeah? Like petrochemical industries, for example. So this is really a good technique, and it is absolutely essential to learn this technique. And if by any chance, if you manage to get a lab access, or if you get expertise or hands-on expertise, like even 1 year of experience with the chromatographic techniques, you have a job assurity. Like many companies like Pfizer or MSD or GSK, all the top or so-called these pharma giants, they love to recruit you if you are an expert in chromatographic techniques. Yeah? So at least if during the interview or something, you can convince them based on whatever the theoretical knowledge that you are gaining at the moment. And I will post a supplementary video on thin layer chromatography, how to perform this experiment in the lab, and just to show, like we talked how the molecules move in the stationary phase, blah blah blah, and so on. So if you look, if you want, we can see that with our naked eye. I will try to make some video, and then I will try to compile them, maybe like a 10 to 20 minutes video, so you will get some rough idea about how the molecules move in the column, how to get the retention factor, and so on. Yeah. So again, back to the topic. Always remember, like if you have a column, if you have A plus B, so if there is, say, like you have a clear separation, something like that. So how to say that, like some molecules that are well separated from one another, in this case. So this molecule A and B, they're well separated from one another. So this will have this type of system will have a high separation factor, high degree of separation, alpha, or separation factor. Or if we take something like that, A plus B, and when the elute close to each other, something like that. So you have some clear separation of B here, and then here you have some A, and somewhere here you have a mixture of A plus B. So what does that states? So if you want, we can say something like these two analytes A and B, they elute close to each other, and in this case your separation factor alpha will be lower. So I hope I managed to explain this part. So let's try to, let's say we have some two experimental outcomes, something like this. Say we have a mobile face, drawing this vertical line for my convenience. So this is A, this is B, this is your mobile face, or let's say this is something we obtained from the tracer molecule. Again same tracer molecule. So this is, say, like this time we used mobile phase 1. Say let's say pure acetone, for example, and this time we are in the second experiment we are using a new mobile phase 2, say a mixture of acetone plus water. Again your retention time is something like that, and then so this time we get some result like this. So in this case we see that the TM, the retention time in the mobile phase, is constant for both the cases, and also the retention time is also same for A and B. Retention time is, so TR is something correspond. So I already talked about this one, TR retention time. So this is something like where you observe your mean concentration on your Gaussian peak. So that will be your peak height, or something the peak maximum, the time that corresponds to your peak maximum, say TR. So if you calculate the separation factor K, it will be the same, TR minus TM divided by TR for A, and also we can do the same for compound B. And if you look for both the experiments, the K value will be same. So the first experiment, so let's put say TM for the first experiment, say 5 minutes, and then TR for A, let's say 10 minutes, and TR for B, let's say 20 minutes, and we do the same. The time spent by the analyte in the mobile phase, let's say same like 5 minutes, and then spent TR for A is 10, TR for B is 20. So for the experiment 1, your K value for A is equal to 10 minus 5 by 5, and then K value for B is equal to 20 minus 5 by 5, and then for experiment 2, Ka is same, 10 minus 5 by 5, comma Kb is equal to 20 minus 5 by 5. 20 minus 5 by 5. Hope I'm doing not any mistake. Something like Kb. So what is this value? 10 minus 5 is equal to 5 by 5, that's equal to 1. Kb 20 minus 5 is equal to 15 by 5, that's equal to 3. Here is the same, Ka is equal to 1, Kb is equal to 3. So what is this? So what we learned from these two experiments, from a simple graph which I shown here. So just to follow the highlighter this time. Just follow the blue highlighter. So if you see the first experiment, we have a clear separation of A, and there is nothing happening, and then something like a B. So your A elutes first and then B elutes second. and this is your tracer molecule that allows you to calculate the time spent by, what will be the time spent by the analytes in the mobile phase. And then if you look at the second experiment, we observe something similar. We observe TR exactly at the same point, but only difference is there is no clear separation. So there is something like a mixture of A and B in this region. So what we learned from this type of, just by looking at the graph, is like for both experiments that retention time is same and your retention factor, even the retention factor is same, but the separation, degree of separation, in the first experiment we managed to achieve something like 100% separation, whereas in the second experiment we didn't achieve that. There is something we cannot separate. So what's the factor that connects? So in this case, what's the factor that you can think by looking at the graph? So in the second experiment the separation is poor, in the first experiment separation is perfect. If you look at this image, just to see the red highlighter, or just see the pink line or blue line maybe, just to see the blue line here. If you see the width, if you see the width in the bottom of here, and if you see the width somewhere here, and then again if you see the width, so both A and B have a common width, whereas you have a clear width of A and in the first experiment, and also separation, sorry, and also for B we have a separate width. So separation factor is something we can relate to. Separation factor, or the degree of separation, we can relate to the width of the peak, or width of the curve, maybe, or how to call it, maybe Gaussian curve. I expect you to listen to my lectures, like some of the students, if you think like you can just look at the notes and you can get over with it and you can answer all the questions in the final exam, it's going to be really tough, because I write in the notes because whatever that comes to my mind at the moment, or whenever I'm thinking to teach something for you, I talk whatever that comes to my mind at that moment, and that's what I write it on the notebook. Yeah, so if I'm going to teach the same lecture tomorrow, I would teach in a slightly different way. I will use a different set of pattern. Obviously I will cover all the topics, but it's going to be slightly a different pattern. So try to listen to these lectures, and you are not going to get anything outside what I am talking in the lectures, but if you just look the notes, then you will get into trouble in the final exam, because in the notes I'm not writing everything that I'm talking in the video. So you must listen to the lectures. So that's the, and this is not like I'm forcing you to listen to the lectures. So the purpose of education is to learn something. I worked in this technique, with this technique, for 10 to 15 years at the moment, so I know it's not an easy technique. Yeah, like so if I can talk everything based on textbook knowledge, but since we working in this with this technique every day in the lab, we know the practical difficulties when it comes to interpretation of data. So that's why I'm going a bit slow, and I'm throwing a lot of information when I am writing something on the notebook. So what I'm writing in the notebook are the key things that you should remember, like formulas, how to solve, how to look the molecules are moving, or how to, if I like just to show you how the stationary phase look like, how the molecules move on that stationary phase, how the mobile phase guide or push those molecules from the column exit inlet to the column exit via the stationary phase, and so on. So those things I need pen and paper. But apart from that, when we are discussing the concepts, I'm throwing some random information. So I might set some multiple objective questions based on whatever the information I'm talking throughout the videos, lecture videos or the tutorial videos, and that's why you have to watch the video. and obviously your final exam is only for 40 marks, and you're going to get the remaining 60 from the assignments and the lab and and other things that you are doing for this module. So to get that 40 marks, obviously you have to do that extra bit of hard work. I think so far so good in my opinion. So I already said what this separation factor is all about. It's something related to the width of the peak. If you want, we can set a question just now, right now. So how to do that? So let's say we have compound A and B. I think I already solved a problem for you. So let's try to calculate the the separation factor for both of this experiment. So alpha will be equal to Ka, no, in this case Kb, because that one eludes second and Ka eludes first. So Ka by Kb, that will be equal to 3 by 1. So 3. Ka is something related to Kb. So this is no, Ka by Kb, that's equal to 3. Yes. So what we have is like we have a separation factor, but if you look at the image here, still we know that in the first experiment we have a clear separation, and in the second experiment there is no clear separation, but still the separation factor is same. So alpha is equal to 3 for experiment 2 and alpha is equal to 3 for experiment 1. So one thing we didn't manage to to, to, to define, or how do you say, like we don't know the resolution. This alpha is not talking about the resolution of the chromatogram, or the resolution of the separation, how well these two molecules are separated. So we need some additional terminologies that will give some accurate information about how well these two molecules are separated. So that's what we are going to cover in the next 10 minutes or so. I'm going to save the video for the moment and then I will continue. I think we fairly covered so far something on the separation factor, retention time, and also what else we saw? Distribution coefficient or constant. And then we also learned what is a retention factor. And we also defined what is separation factor or a degree of separation and so on. So these are the few parameters that you have to remember. And then few more things. I'm just checking what we covered so far. Yeah, and one thing is like we don't know how to quantify the resolution, so that's what we are going to cover now. So if you look at the graph which you are seeing at the moment in the screen, as I said, like in the first graph or in the first experiment, just to follow the pink highlighter, as you said, like we have a clear separation in just follow the pink highlighter. So we have a clear separation here between compound A and compound B, or if you want we can say molecule A and molecule B. And then again in the second experiment we see that A and B are clearly separated if we talk only in terms of time. So we have some time factor with molecule A, just to follow the pink highlighter, and then we have some time that retention time that corresponds to your molecule B. So if we go back here, so So we already defined, say like so let's draw this one. Say this is for your compound A. Maybe let's strike it and draw it again. See, this is for your mobile phase TM. This is for your molecule A. So something we can call it as TR of A, and then say we have some molecule B. So this is the retention time for molecule B. We have, so this is our chromatogram that we obtain by performing some experiments. So let's put it like that. And from this one, so obviously we can calculate what is our, we know the retention time. So we know the retention time of your analyte A in the stationary phase, and then we also have the retention time of analyte A and B in the mobile phase. So from that we can calculate the retention factor K value, which you know how to do that. Let me check what we saw in the previous. So we can calculate the retention factor. So we know K is equal to TR minus TM divided by TM. So this is nothing but TS by TM. So, and then we can calculate this retention factor for A, and then we can calculate the retention factor for B. Again, TR minus TM divided by TM for molecule B. That should be equal to retention time of molecule B in the stationary phase divided by the retention time of molecule B in the mobile phase. So from this we can calculate separation factor, which is nothing but alpha is equal to, in this case, KB by Ka. So I hope you all understand up to this point. So one thing we can know is like this retention factor which is Ka or Kb, also, or the separation factor, which is in this case alpha, or if you want we can call it as a degree of separation. It can, all these values will roughly tell like how the center of the two peaks are separated. So in this case, if you come back here in this graph, just follow the pink highlighter here. So we know the time here, TR for A, and then the retention time of molecule B. So if these values are separated from each other by a bigger distance, then your Ka value will be higher. Sorry, your alpha value will be higher. So let's go back to this formula. So what do I mean by that? So if we have some chromatogram like that, say for A and then for B, so if this distance is higher, then your alpha value will be higher. And then if you have another chromatogram, say this is for A and then another one, this is for B, and if this TR value, the difference between the retention time of A and the difference between the the difference between the retention time of A and B, if the difference is less. So let's continue with the topic. So what I was talking is like if the separation the retention time between these two compounds, say molecule A and molecule B, and the difference between the retention time, if it's less, then alpha value will decrease. So what this alpha, or even your retention factor, for example Ka, this value, so this value will be higher. This value will be higher if TR minus TM is higher. So, but anyway, since we are talking about separation, we should consider about compound A and compound B. So we are separating these two compounds. So one factor that connects these two parameters is alpha. So this value will increase if the TR A minus TR B increases, and alpha will decrease, or the separation factor will decrease if the TRA minus TRB decreases. So this gives some general picture about your separation factor and something related to your experimental outcome. But one thing which is clear from these two from the definition of alpha is like if just look at this picture before saying something about that, about the resolution or something like on that line of resolution. Just look at this picture for one time. If you look here, so in both the cases we have a clear separation, so separation is very good. In this case as well, that is, separation is very good. So imagine if you have something like a one which I'm drawing now, so time. So this is our mobile phase, retention time in the mobile phase. And say this is TRA, and then let's say we have something like that. This is compound B, and let's say this line is TR B. Even for this case, we can calculate alpha value. Alpha value will be just equal to KB by KA. So still we can calculate separation factor, and that's because we have some difference between retention time of A and retention time of B. So one thing we understand just by looking at these graphs, say let's call this as figure 3, and let's call this as figure 1, and let's call this as figure 2. So from figure 1, 2 and 3, one thing we can understand is like alpha is a good parameter, separation factor. It more or less it's like indicates how the center of the two peaks are separated. So this is our, just to follow the highlighter. So this is one center of peak, and this is another center of center of peak for molecule B. So your alpha value tells how these two peaks are separated. However, it does not tell any story about how the tails, whether they overlap, tails of this each peaks. Say this one, just to follow the, this time follow the blue highlighter. See this tail and then this tail, how the tails of each of these peaks overlap. So the factor alpha, separation factor, it cannot capture such information. And always remember in the mind that chromatography, we use chromatographic technique. The main purpose is to separate molecules rather than playing with the column and then trying to get the retention time of A or B or so on. Yeah, so the first objective, like for crystallization, the main objective is purification. Like so for chromatography, the main objective is the separation of the molecules, and also to get some pure products. Normally we get a pure product if you manage to separate all the individual components from a sample mixture. So that's the whole idea. So that's why we need another terminology, like we can call them as a resolution factor, or we can say chromatographic resolution. Chromatographic resolution, something like that. So what is this? This chromatographic resolution, it can measure the extent. It can measure the extent to two peaks are separated. Or if you want, we can tell this one factor, it can characterize how well the two peaks are separated from each other. And then it also take into account of the width of the each peaks. So how to define this resolution factor? It's an analytical expression. So say like in this case we have molecule B and molecule A. So let's say residence time of molecule B minus residence time of molecule A divided by the width W2 plus W1 divided by 2. So what is this W2? So W2 is the width of the, or if you want we can say like B and then WA. So WB is the width of the peak that corresponds to your molecule A, and WA is the width of the peak A, or width of the, how do you call, width of this Gaussian distribution curve that corresponds to your molecule A. So I hope you all can understand up to this point. So if you want we can rewrite like, you put the 2 in the numerator, TRB minus TRA divided by WB plus WA. So if you have a chromatograph like this, let's say molecule 1, this one, and then let's say molecule 2. So we know the retention time of molecule 1, and then we know the retention time of molecule 2 from this type of chromatogram. So we can calculate the resolution or the chromatographic resolution, which we can define like in this case TR of 2 minus retention time of molecule 1 divided by width of the Gaussian peak that corresponds to your molecule 2, and then the width of the Gaussian curve that corresponds to molecule 1, and then you take an average of these two. So in this case you can write like this one, TR2 minus TR1 divided by W2 plus W1. So I hope you all can follow up to this point. So if you come back to, okay, if you look at this figure, let me change it to highlighter, just to follow the blue highlighter. If you see here, you have some clear baseline for molecule 1, and then you have another clear baseline for molecule 2. Or if you want, we can, if you want to say in the words, we can say like, if you look at this chromatogram, one thing which is clear is the baseline separation is how do you call, is complete. How do you call, like you have a baseline for this part of your chromatogram, and then this baseline is separated from the baseline of this Gaussian curve or this Gaussian distribution. Or if you want, we can tell the peak. We have two peaks here. So you see, we draw a baseline, and then this baseline is separated from the baseline of the next molecule. So how we can say like in this case separation is complete. But if we take another case scenario, say like we performed an experiment, say time in the x-axis, and then we have something like this. We'll now follow the pink line or blue line. Maybe put pink, it's more visible in the screen. So if you see this baseline for molecule 1, and then there is another baseline for molecule, follow the blue highlighter. So this is the baseline for molecule 2, and then follow the red highlighter. This is the baseline for molecule 1. So what we see is like the baseline is not clearly separated, so which means the separation is incomplete, or if you want we can say like we can say like the analytes, the separation of analytes is not fully resolved. So you can say like no clear separation of the baselines. So in this case your RS value will decrease or will be low. Or if we go back to this figure, in this case we have a clear separation of baseline. In this value your RS value will be higher. So I hope so far everything is fine. So by the way, this figure we call them as a chromatogram. I don't know whether I said this in the previous lecture. So I hope until this point everything is fine. And whatever if we have a chromatogram, we call them as a peak 1, peak 2, and then whatever the width we have under each peak, we call them as peak width, and then if you want we can call them the maximum height that connects the peak maximum with the baseline. The distance we can call it as a peak height. These are some terminologies that you should remember when you look at a chromatogram. So I hope so far so good. I know we are going very slow, but resolving a chromatogram is not easy. Yeah? Normally there will be some old guy with a lot of gray hairs in the company. He will be the guy who is dealing with this type of. He will look at the chromatograms and give some suggestions which part should be improved in order to achieve a desired separation. So this is like really a topic for experts or someone who have significant amount of experience, and we are trying to learn everything within 2 to 3 lectures and plus some more tutorials. So that's why I'm going a bit slow. I think with this formula we can calculate the resolution. So maybe we can try to solve a few problems. I will try to take some HPLC chromatogram from the internet, and then from there we can calculate the resolution factors. And typically there is some ideal value. So if you have a chromatogram like this, so if your column if your peaks are clearly separated, or which means we achieved a molecular separation in that column. So what does that mean? And in this type of cases, typically if the RS value will be more than 1.5. So if the RS value is more than 1.5, that or 1.5 to typically in the range of 1.5 to 2.0, that indicates clear separation. If the RS value is less than this, then probably, how do you say, like if RS value is less than 1.5, then probably one of the tail of these two peaks may overlap with each other. So which mean so there is no clear baseline separation, which mean we didn't manage to separate those two molecules or two compounds from their mixture using this particular technique. I hope you all understand up to this point. And then this resolution, so this is some expression that allows you to calculate the resolution, chromatographic resolution, or you can call it as a resolution factor. And this RS value, it depends on few parameters. One is we already know, retention factor, K value, and then it also depends on separation factor. We already know what is that, and then it also depends on one more value. It's called the number of theoretical plates. This one we will cover in a separate lecture. Number of theoretical plates. So chromatography is it's easy if you know, if you understand, or if you know how to read the chromatogram, and if you know how to calculate the values and so on. And apart from that, which type of solvent to use, these things you need a bit of experience, and you should know some chemistry knowledge. You don't need to be a superstar in chemistry, but some basic knowledge about solubility, and then something like the different type of energies involved during adsorption. This type of knowledge is more than enough to select which type of solvent we should use, and something about the polarity factor and so on. We don't have to cover all those things for this module. For this module, we are covering the engineering aspect, and in fact in the first lecture I already talked about how the solubility affects, and also I already talked about the adsorption and desorption processes, and I also said what is the driving force behind everything that's happening, especially the molecular movements within the stationary phase, and from mobile phase to stationary phase, or back from the stationary phase to mobile phase. We already covered all those things, and we already learned a lot of things, like a lot of factors or terminologies involved in chromatography. And the one thing that we need to learn is the number of theoretical plates. So this one we will cover in the next lecture. But for the moment, I'm going to write a formula. This RS value depends on all these factors: this retention factor, separation factor, and the number of theoretical plates. I think in the lecture 7, I think I already talked about the number of theoretical plates. I gave some rough idea, like if you have a column. I already gave a rough idea, like if you have a column and there is some adsorption, desorption, and then it happens so if you have one adsorption event, second, third, fourth, so you can call each of this equilibrium stage as theoretical plates. So each of this equilibrium stage we can call like one theoretical plate. So if you have more number of theoretical plates, so the separation will be even better. So that's the meaning of number of theoretical plates. But this is not that simple. We have to consider a lot of factors before explaining, or even use this word number of theoretical plates in the sense of chromatography. So we will cover this in the next lecture, but these are the things you should keep in your mind. So I will write the equation here somewhere in the corner. The paper tube software which I am using, it won't allow me to type or write more than I don't know how many number of pages it can take. So I would just write the equation here. Separation factor is equal to 1/4, and you say in this case, say this is your molecule A and this is your molecule B. So molecule B elutes later, so Kb divided by 1 plus Kb, alpha minus 1 divided by alpha, multiplied by square root of n, where n is the number of theoretical plates. So the resolution depends on so many factors. One is your retention factor, and then your separation factor, and then your number of theoretical plates. So we will calculate we will make use of all of these equations, and when we will try to solve a few more problems. So I think it's enough for the moment. Maybe we can, so give me a second, let me check. So if RS value is equal to K2 and also alpha minus, I think it's enough for this lecture. Yeah, I don't want to confuse you more. I think we already fairly covered this topic, like in fact we covered even the slightly advanced topics in chromatography. So I know if I give you some chromatogram, you will know to calculate most of the parameter that allows you to characterize the column that you are going to use to separate some compounds. And if I give a chromatogram, you will also know how to calculate all the parameters like retention factor, separation factor, and also the resolution. Resolution is very important, especially if you talk about chromatography. And then in the next lecture, I will show you, I will explain something about the number of theoretical plates, and then we will try to calculate. So if I give you a column, we will learn how to calculate the number of theoretical plates. That's not a big deal. It's very easy. You already know the outcome of the, how do you call, the experimental outcome from a column chromatography is a Gaussian distribution curve. So if you know that, if you keep that, my results will be in the form of a Gaussian distribution, then you will know how to calculate the number of theoretical plates. It's not at all tough one. It's really easy, but it involves a bit of mathematics. And then the number of theoretical plates, it also changes with so many parameters, like the size of the, how do you call it, the properties of the solid or the packing material which is inside the column. It also changes with how your molecules are moving from within the column, from the inlet of the column to the column exit, and then also how the molecules are moving from the how do you call, from the middle of your column to the wall, to the column walls. So there are few other parameters that we have to consider. So those things we will study in the next lecture. So next lecture will be slightly bit more advanced topic, and after that we will quickly show some theoretical part, like different types of chromatography, and where do they use, and what type of molecules we will separate using those different type of chromatography. So I think this is more than enough. And as I said in the beginning of this lecture series on chromatography, we will cover only the elution chromatography and liquid chromatography. We will not cover anything about gas. So for that you have to take separate module, something on analytical chemistry. But I think this knowledge is more than enough. So I will try to get some problem, something related to pharmaceutical engineering. Then I think that's enough for the moment. So thanks for listening.